I don't see the record thing. It actually is recording. Why is it flickering that way? Let me hit pause and then start again. There we go. So we're back recording again. Okay, great. Okay, this is ELC 111, and it is October 27, 2020, and we're going to cover Chapter 8 on electrical conductors and wire sizes, and then we're going to try to work in some lab time. So we'll go ahead and get started. Okay, get back to here. Okay, so Chapter 8 in your book, we're going to look at factors that determine the resistance of a conductor or a wire, and we're going to use wire gauge tables. Now, we're going to look at total circuit resistance in circuits, and it has 5 components to it, and it's a little more to it than what we've looked at. We're going to dig a little bit deeper, more on the engineering level. So the total circuit resistance is determined by the number and type of components that you have. Also by the type of the circuit arrangement, such as series or parallel or combination, and the resistance of your switching and control components. We have not looked at that, such as a switch. A limit switch or a push button can have a little small amount of resistance to it that can actually become a lot of resistance. You can have a wall switch over there that after a lot of years, it builds up more resistance from arcing, and it can actually produce dim lights because of too much resistance in a switching component. So you can have problems sometimes because of a switching device that's actually got a lot of buildup from arcing and all, and it's pitted contacts. So that's where that third one can come in. Or problems with circuit breakers, that can give you resistance in your control area. And then the resistance of the conductors carrying power to the components. That's one that we're going to get into today, is that the wires itself that go from your switch or so on out to the load, the resistance of those wires, it starts to matter when you go hundreds of feet, like on hog farms, places like that Jamie deals with all the time. You may be, what's a typical distance, Jamie, from the highway, from a light pole out to a hog house where the power comes in? How far could that typically be?
Yeah, typically it's pretty good way. Usually 100 yards is about close.
100 yards, okay. So that's times a yard is 3 feet, so it's a lot. And he said at least that far. When you start getting in that kind of length, the resistance of the wires matter. You start getting something called voltage drop, and that matters. You got to calculate all that in. So this chapter and Chapter 9 are going to help you to get a full understanding, so that if you had a hog house way off the highway, and you knew the total amp load of that building, you can actually put the footage into this formula, the footage in, the amps you got to have, and all of that, and that formula will tell you the wire size you got to have to keep from having too much voltage drop. So that formula comes in Chapter 9. That this chapter gets you ready for. Then internal resistance of the voltage source. That last one, we're not really going to get into that. That's a little deeper than the scope of this class, but it is an issue. It can be. The power supply itself can have some internal resistance that might limit, that can come into play with the total resistance of a circuit. Now, in terms of the arrangement, when you look at the total resistance of a circuit, say that total resistance depends on the arrangement of the components. Here's what we're talking about. Here you've got 3 resistors that are 6 ohms apiece, right? You've got 3 of them here. You have 3 of them here. You also have 3 here, right? It's the same 3 resistors, but they're arranged differently. So depending on how you arrange them, it's going to change the total resistance. Here, 3 of them in series, you have a total of 18 ohms. Y'all agree with that? Because it's series. Here, you take those same 6 ohm resistors and put them in parallel, and you end up with 2. The simple way to figure that would be resistance of one of them divided by however many of them there are, and there's 3 of them. So 6 ohms divided by 3 would give you 2. Now, they're matching. So that gives you a total resistance of 2 ohms. You see how drastically different that is. That's what they mean by the arrangement. And then when you do a combination, you put 2 6s in parallel to give you 3. And then that 3 in series with that 6 gives you 9. So they give you 9 the way that is. Now, the conductor resistance, which will be the resistance of the wire itself, that's what we've never looked at that we have to get into now. Because wire does have so many ohms of resistance to it per foot. It's a very small amount, but it matters on long runs. So conductor resistance depends on 4 things, and these things are in your worksheet. I got a worksheet in Moodle, and it's going to ask you things about, everything we're talking about. So the worksheet is in there. I put it in there last night. So your conductor resistance depends on the material that's used, such as it could be copper wire, it could be aluminum wire. That chart that I showed you, if I go back to that, and let me make sure I'm switching my screen share to make sure whoever's out there would see it. Okay, so here you have these 3 columns show copper wire. These 3 columns show aluminum wire, or it could be copper coated or copper clad aluminum. But they don't get into the resistance here, but it is in the code book. It's just to show you that typically, if you're dealing with wire, it would be either copper or aluminum. Most of the time, copper. Aluminum is used sometimes on mobile homes for the power, or feeding the power to the mobile home, or it can be from going from a house out to a garage. If somebody's going to do a building or something, a shop, people typically go out and buy aluminum wire because it's cheaper and it's lighter weight. But you got to go bigger in diameter to get the same amp capacity. So you have to go bigger, but you still save money. But that's just an example there of the material that's used. My laptop's got a little lag to it today. It's got a little lag like me. All right, so the material used can be, it's whatever the wire is made out of. And some things, like in some high dollar connections, some connections can be gold plated. Some can be silver. Some connections can be silver plated, gold plated, in some really high expensive electrical connections. So gold is a better conductor than copper is. And but of course, who can afford to have? You can't buy gold wire, but gold plated connections are, they have those in computers, in some computers. And then the length. So the longer the wire is, that's the main issue we're going to be looking at today as far as how much resistance that you have in wire is however long it is. Because if you got 100 foot of wire and it's got so many ohms, if you double it and go 200 feet, the resistance is going to double. It's going to exactly double. So your resistance goes up directly proportional to the length. And then the cross-sectional area. The cross-sectional area of the wire would be, when you slice the wire and you look at the strands in there, if it's stranded wire, That would be the cross-sectional area of a piece of wire there. So the bigger that cross-sectional area gets, the lower the resistance, because it's like a big pipeline. So if you can figure, if you had a pump and you were pumping water through a 1-inch line, and then all of a sudden you increase it to a 4-inch line, the pump can actually give you more flow, right? Because it's a bigger line, there's less resistance with a larger pipe. It's the same way with wire. So if you go bigger on wire diameter-wise, the ohms goes down because it's just a freer flow. There's less resistance when you go larger. The longer you go, the higher the resistance goes. But the larger you go, it goes down. So you can just relate it to pipes, you know, and it's the same thing. And then the temperature. The temperature in the area that you're at is going to affect the resistance of the wire. So let's say, for instance, that I've got wire, you know, the wire that's going to a pump, and today it's 70 degrees ambient temperature. Let's say if it gets up super high, around 100 degrees, the resistance in that wire goes up a little bit, a small amount. When the temperature in the area goes up, then the ohms, the resistance in that wire does go up a little bit. Now on materials, silver, it says silver is the best conductor. It's expensive. Copper is good, fairly inexpensive. Aluminum is used to reduce weight in some cases. And then they use alloys for heater elements. So for heater elements, you know, like in our water heaters and so on, and on your stoves and your crock pots and coffee maker heater element, you've got the toasters. Everything we love to have to cook food's got heater elements except microwave. So in here you got alloys. That's an alloy of different kinds of metal. That they'll come up with like a mixture to give you so many ohms to make some resistance to generate heat. So in here you got, that's about 16 ohms there. And it really gets hot now when you put 240 on there. It just gives you some good hot water. You take a shower, that will wash dishes. So that's where the alloy comes in. They have to do alloy to give you a controlled amount of resistance and a controlled amount of heat. It's a very special chemistry and all that goes into that. So that's what they're referring to about that. The length of the wire, resistance is directly proportional to the length. So 2 feet of wire has twice the resistance of 1 foot. And 3 feet of wire has 3 times the resistance of 1 foot. Cross-sectional area. It's called CSA. That's an abbreviation, CSA. The larger the cross-sectional area, the lower the resistance. Cross-sectional area is measured in circular mils. And it can be found by squaring the diameter of the wire that's in thousandths of an inch. So the basis of what we're going to be doing right now for calculations is based on something called a mil foot. And a mil foot of wire is this. It's one strand of wire that's about like a piece of hair, that it only measures 1/1000th in diameter. So if you measured it with a micrometer or a caliper, that piece of copper wire would only be 1/1000th of an inch in diameter that you could actually measure. So when you square that number, it becomes the circular mil. And that's what we use in our formulas is circular mil. So a basic unit for doing these calculations is that if you got a strand of wire 1/1000th wide, 1 foot long, is called a mil foot. And they're going to give you so many ohms. There's going to be a rating on there to say that copper wire has so many ohms per mil foot. So when you strip that wire down to 1/1000th and it's 1 foot long, it's going to have X number of ohms to it at a particular temperature. at a particular temperature. And when you change that temperature, and they're always going to tell you what that temperature is, they'll say that copper wire has 12.9 ohms at such and such temperature. If you lower the temperature, the resistance goes down a little bit, and they're always going to tell you the ohms and the temperature before you have to do a calculation. To calculate the resistance of a piece of wire, the resistance of that wire is going to equal this. There is a K factor, and this K does not mean thousand. If this one time, the K does not mean kilowatt. K is a constant factor that represents the number of ohms of a mil-foot of wire at a particular temperature. So here, they're starting out saying that copper wire has 10.4 ohms if you have one little tiny strand that's a mil-foot. It's only 1,000 strand, 1 foot long. It has 10.4 ohms at 68 degrees Fahrenheit. It has 12.6 ohms at 167 degrees Fahrenheit. So that resistance goes up as temperature goes up, and this is the basis of our calculations. You have to know when you're going to calculate the resistance of a piece of wire, what temperature are we at? So you would put the K factor in there. If a K, it would either be 10.4 or 12.6 at this point right now, from what they're telling you. You'll see that go up to 12.9 at one point at a higher temperature, but it'll always be given. So the K factor would be this or this. L is going to be the length in feet of the wire, and then CM is going to be the circular mils of a particular wire size, and you get that off of a chart. So this chart here in your book, does everybody have a book? This chart here see if I can manage. Yeah. The wires that y'all have worked with out here on your boards were number 14 AWG. So number 14 AWG has a diameter in mils of 64.084. But the circular mils, when you square that, the circular mils is 4,110 circular mils, and that would be the number you would use in the calculation. So 4110 would be the circular mils that you would plug into that formula that we just looked at to calculate the resistance of that wire at so many feet. Okay? And then it tells you for a number 14 wire, look over here. You have 3.07 ohms if you have 1,000 foot. So what it means is if I had a 1,000 foot roll of number 14 wire, a brand new roll, 1,000 foot long, and I took both ends of that wire, that roll, and I put an ohm meter on there, and I measured the ohms of that whole roll. The entire roll would read 3.07 ohms of the actual number 14 wire, 1,000 foot of it. So that's a standard thing that they actually tell you from the manufacturer, the resistance of the whole roll, okay? And if you go to a larger wire, a number 12, for instance, is bigger. Your circular mils is bigger, and the resistance goes down. So 1,000 foot of that would only be 1.93 ohms. The bigger the wire, the less the ohms. If I go down, say, to a number 10 wire, then it's only 1.21 ohms for 1,000 foot. So you see how that goes? And it goes down, 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 down in resistance as you go larger. You see how that goes? 1,000 foot of a number 1 AWG is only 0.154 ohms for 1,000 foot. So the bigger, the less resistance. Everybody cool? So when you go solve a problem, this is one of the go-to charts right here. That's one of the go-to charts. excessive current can raise the temperature, and it may increase the resistance. Which means that if you overload a wire, if you pull too many amps through it, it's going to get hot because of the resistance in it. If you go above the ratings in the chart that we looked at, then it's going to get hot, hotter than it's supposed to, and then it's actually going to affect the resistance of the wire. So it's going to be a domino effect if you exceed the ratings of a wire. And just for instance, if you go back to that wire chart, go back. So when we go to this, back to this chart, a number 14 wire, if you have a number 14 wire that's rated at this temperature here, and let's say a number 14 wire that's copper, it can have a temperature rating of 140 Fahrenheit, 167 Fahrenheit, or 194 Fahrenheit. Those temperature ratings are actually based on the insulator, not the copper, but the actual insulation around the wire. The copper itself can handle way more, okay? So it's not a temperature rating of the wire, it's actually the stuff that wraps around it, okay? So, and you'll see there'll be letters that will be stamped on the insulation that's going to tell you the type of insulation. These letters here, RHW, THHW, those letters mean something. Like the THHW means thermoplastic, and the two H's means certain temperature range, and then the W means for wet location. So T is thermoplastic, W is wet location, so on like that. And the X would mean something about the type of the type of material it is. All that stuff means something as far as insulation type. So again, the copper itself, if you notice, if you have an insulation of this type, then you're limited to 140 Fahrenheit. That number 14 wire can handle 15 amps only. Now, that same number 14 wire, the same amount of copper, but a different insulator around it, can actually handle 20 amps if you're using this type of insulation here. If you buy that type, it can handle 20 amps. That same number 14 wire can handle 25 amps if you buy this type of insulation rated at 194 Fahrenheit. There's no difference in the amount of copper. It's the same amount of copper in there, same size, but the insulation is different. And the insulation can actually make that overall size be fatter, to be bigger, because it's thicker insulation. So if you see two pieces of number 14, and you know one of them is bigger than the other one, it's not the copper that makes the difference, it's actually the insulator that does. It's either thicker or thinner. And it goes the same all the way down, no matter what size you're at. If you got better insulation, you're allowed to go higher on amps. Switch my screen sharing each time. A little lag in there. It didn't switch. Yeah, my computer's sluggish today. Okay, so excessive current, you know, if you go above the ratings on that chart, you're going to overheat that wire. And again, that's going to give you a side effect of the increased resistance if you don't stay within so many amps. That's kind of, Jamie, what you said. You had somebody was trying to use a number 10 wire for a 50 amp welders or 50 amp pressure washer. Somebody on the hog farm is trying to use a 50 amp pressure washer through a number 10 wire. And the number 10 wire, if you look on that chart, what do you see for what's the amp rating? Let's just use that for an example. Let's just actually look at that. I'll switch back to the wire chart here. Now, so in Jamie's case there, I'm gonna pick a middle of the road wire type. Will you use a raw mix cable or just when you use the stranded wire?
It was
THHN. Okay. Now here's another thing you got to be aware of, and let me get something to show you an example of that. There's a limit. Let's say, for instance, you would use a THHN wire, okay? Now, THHN wire. Now, that THHN wire is rated for 194 Fahrenheit. It's rated for that, no more than that. If you go above it, it's probably going to melt the insulation down. Now, so the THHN, and it's a 50 amp circuit. Okay, so if you go straight down, it would have to be a number 8. A number 8 wire. Now, here is the catch. You can use a number 8 wire for 55 amps only if that the terminals that you connect to are rated for this, either 90 degrees C or 194 Fahrenheit. Now, I'm going to show you an example of a motor starter here that's rated for 75 degrees C as far as the connection. So the connections that you tie to your terminals can cause you to have to go back another column, even though you have that kind of wire. Let's see in your case, if that pressure washer, if the terminal's on it or the terminal's on the breaker. Breakers have also ratings on the temperature rating. Okay. Let's say it's a circuit breaker that you tied to a feedback receptacle. If that circuit breaker terminals were rated for 75 C, then you couldn't use this column. You got, even though it's that kind of wire, you got to fall back over here and come down and say, then you got to go, what size wire would you have to go to then? Actually, it's the same. It's still a number 8 in this case, but you couldn't pull no more than 50 to where over here you can pull 55 amps. So it cuts it down by 5 amps because of the insulation, because of the limitation of the terminals that you're tying to. That stuff will be stamped on whatever device it is in most cases. I'm going to pass this around. And you can see that where it tells you way over here, it says for your wire connections, anywhere from the number 10 to 18, CU, and that's copper, CU is copper, 75 degrees Celsius. And that's the rating of the terminal. That's the limitation, but you see that. So even if the wire can handle, even if the wire can handle this, the weakest link in the circuit can be the terminal, and you got to go back, whatever the terminals are, go back if it does. Now some terminals are rated for this. I've seen some that are, and then some are not. So you have to follow that. That's actually in the code book that you go by whatever's the weaker in the circuit, the terminals. You have to look at the terminals on both ends of the wire, where the breaker is and then where the receptacle is, and then follow that column. Okay. Everybody okay with that? And I have to get you a copy of that section in the code book that says that. The code reference is 110.14. If any of you dig into the code book online, you can look at the code book for free. But I'm going to copy of that. This article 110.14 is what it tells you what we just said. And that's one that can catch you in the rear whenever you're answering questions on state tests. That's one that they really try you on there. Right. There's something going on in the background. My computer's got some lag to it. Okay, go back up here. Okay, so that's the last slide there. Now we're going to do some examples. We're going to go through and do some things, some examples of the worksheet, so that you can know how to get started with this. Okay, so get you. How you doing, bro? All right. Let's go back to. I want to be able to keep that up there and then give you, let me just do it this way so we can have everything together. On the screen. Switch so much. So let me ask you a question here. The resistance of a copper conductor is inversely proportional to what? Either the CSA, cross-sectional area, or gauge. Hold on, let me just pull it up. I'm going to have to pull it up so you can see what we're looking at here. Let's pull. I'll have to do a screen switch here. Stop share. Back to get back up to there now. Okay. Back to there. Now I'm back to the welcome mat now. Let me do a screen switch. Now I'm going to share that screen so everybody can see what's going on. Whoever may be watching. Little lag here. Now I'm screen sharing that with whoever's watching. So when we go down to the worksheet, it's right here for chapter 8. So let's just go in there and look. Yeah, I think, let me see if I can enlarge that. Now, so let's just go through some of these. I want to hit the high spots on the ones that can really be a problem for y'all, okay? So the resistance of a copper conductor is inversely or opposite proportional to what? What's the actual best? Actually, no, because the gauge numbers, as the wire gets bigger, the numbers get smaller. You know what I mean? If you look on the wire chart, so that, if we think about it real good. Yeah. But if you, in other words, if you, let's think about it like this. If you go from a number 14 wire to a number 12 wire, the resistance goes down, right? The resistance goes down and the number gets smaller, but the wire gets bigger, but the resistance is going down, right? Because in this range here, from 18 gauge down to 1, as the numbers get smaller, the wire gets bigger each time, right? So those numbers would not be, they wouldn't be inversely proportional to the resistance. Yeah. The size of the wire would actually be which one of these, the real size. Not the gauge number, but the real physical size of the wire is going to be which one of those 5. Yes. Yes, sir. The cross-sectional area. The cross-sectional area is really what you meant to say. Is the real size of that wire is the CSA. The gauge number doesn't correlate really, because again, when you go from 18 down to number 1, as you go down in number, the wire gets bigger. So you can't go by that. Yeah. Does that make sense?
Is that what you're saying?
Hmm?
Is that the answer to CSA?
Yes, it is. A conductor has a resistance of 6 ohms. A conductor of the same material and length, but twice the CSA, will have a resistance of what? Now we're not talking the length getting doubling, but the length being the same, but you actually doubling the CSA, okay? Doubling the cross-sectional area. So we got to put some real numbers into this. Hey, Brandon, how you doing?
Hello.
Hey, how you doing?
Doing all right.
We've been recording from the beginning, so you can go back and watch it from the beginning. We have been covering a lot of important stuff. Meat and potatoes.
Right.
Don't mention meat and potatoes. Go back and eat every one of them.
Okay.
Victor, that's what Russell calls it, meat and potatoes.
Baked potatoes.
Meat and potatoes.
Oh, meat and potatoes.
Yeah. When you get into the good stuff, it's meat and potatoes. Yeah.
Yeah.
All right, now. So let's take a look here, and I'm going to switch over to the webcam for whoever's watching. That will be for you.
Mhm.
So our Brandon, do you see the board here?
Yes, sir.
All right, good. So here's what we're doing. You know, we've got a wire of a certain size, and then we're going to double it. We're just going to go bigger on wire, but the length is going to stay the same.
Yeah.
Let's just give you let's put a formula up here that's going to go with that. So the resistance R is going to equal the K factor times the length over the cross-sectional area in circular mills. Okay, this is the formula we looked at. This it's on page 68. Okay, so if you have, no, we're saying here that the conductor has 6 ohms in one case. So in one case you have 6 ohms equals, and we don't know what the K factor is or the length or the circular mills, but we just know that we have 6 ohms, right? We know that much. That's all they're telling us right here. So if you happen to double the circular mills, now tell me what would happen here. Regardless of what these numbers are right now, if I double that number, what's it going to do here? What? It'll reduce it by a factor of what? In half, exactly. So what you got to look at is if I take that bottom number, which would be the circular mills or the area, if I double this, no matter what it is, that's going to become what? How many ohms? But simply because you're doubling that bottom number, and it doesn't matter what any of these factors are, you just know that's what it's going to happen. So when you double that CSA, the circular mills, that resistance is going to go down in half. When we looked on page look on page 69. Look on 69. And it's telling you the resistance in that column over there. As you go to a larger wire, the resistance goes down, right? And we know that. So if you double the size of it, then what's going to happen? It'll go down. Okay. Okay, so any questions about that? Is it clear to everybody or not? If it's not, you can just say the word and I'll help you. You got to have that formula. What I do when I give you an exam in person, I actually give you the formulas. I give you a formula sheet. So what I'm going to have to do up front is give you a physical formula sheet that you can use. And whoever's in here, I'm just gonna have to tell Barney that you're allowed to use them. You know, you can't do it without them. I mean, nobody can memorize all that. You know, you can't physically use the book, but you can certainly use the formulas. You've got to use the formulas. That nobody can. I don't know anybody can memorize all that. So let me make a note here that before I finish up the last thing, I'm going to hand you paper copies of the formula. Of all the formulas you got to have for the exam, and you have that. You use a calculator. That's the only way to be able to do it. What I may do, I actually could embed the formulas in there with the problems. That's probably going to be the easiest thing to do, is if I actually put them in the problem and put the formula with the problem. You know.
My thing is, you got to wait for experience search.
Mm-hmm.
So you're trying to find resistance. It's slow to reach the food. I can't. How was it?
What I can do, I can just make some paper copies of the formulas, and plus I'll try to, and I can put them, embed them in with the question to where you see the formula with the question. You know, I can go that far and do that. I haven't picked how many. It's going to be a new exam, because normally we would have already done 3 tests by now. We haven't done any tests. So the exam is normally the last several chapters. This time it's going to be a little bit off each one. It'll cover some of all of it. So it's going to be a different exam than what anybody's done, because we haven't done any tests. We haven't done any. We focused on that, and we've done some book work, you know, and we haven't done any tests. In any classes I've had, I haven't given any tests this semester, 0. So the exam is going to be a sampling off each worksheet. You'll need to study your whole worksheets. It'll come off the worksheets. Yeah, you need to print those. I would print them, and then that'll be your study guide. You go into review.
I don't think I could review mine after I did mine.
You can't go back in and see them. I mean, some people tell me they can.
No, that's what me and you were talking about on the phone. Once you click back on it, but if you go to your grade, well, just show us how to do it.
Well, as a student, I can't do it from a student viewpoint to see even what you're seeing, because we really need to see it from your viewpoint. I mean, we need to see I need to see what you're seeing. So I can't see what you're seeing. If you hit the review button on the right, then you can go back and see it. And you can hit print, right click and hit print, and hit print. If you right click and hit print, it'll let you print. Once you've got it open, you got to open it up first, and then you can print your You want to go back into open it up and look at it. Now, within there, right click. Go down further into the oh, yeah, now right click. That's it, print. What we can do, we could actually, I'm showing that. On top of here. Let's try plugging it in. Let's try plugging it in so they can see what you just did there. Put now watch what he's doing here. This is how you can print your worksheets. I like that. You got that. And man, Roger, you cool though. I ain't kidding. Let me hold that right there. Once you get it set, where's a comfortable spot for you to get? I'll put the camera where you are. You want to maybe go?
No matter as long as you can see it. Sorry for the high quality too.
Now y'all watch what he's doing. Let's get the glare off of it right here. So watch closely what he's doing here. He's going to go in and open up a worksheet. And watch. You see that review button over there? And then scroll down a little bit. Scroll down into it some, and then right click, and you'll see print. And now go ahead and hit print. And then it's going to show you a preview. And if you hit print, it's going to print the whole thing. Now listen, watch this. If you don't want to print it on paper, print it to a PDF and save it. Watch this. Let's show them how to do a PDF and save it as a PDF. Right, let's get this over with it and see better. Now y'all watching good? When you go to print, instead of printing to a printer, you can hit save as a PDF. And then you would pick some folder to put it in and give it a name, and you can actually save them electronically. Okay, you can do them that way. You can actually do it on your phone that way and save them on your phone. Give them a name. You can set yourself up and save every one of them on your phone as a PDF, and then you've got a good review right there on your phone, and not even have to print it. You need to do that soon, though. Go ahead and all of them that are ready, go ahead and do it. And that's going to be your record right there. Probably I still print them, but what I do probably is save them as a PDF, put them on your phone, and also print those PDFs. Print them. I'd think that was excellent. I like the camera thing. He always get me to plug in the cable, and that's what was afraid of. Yeah, you guys are awesome. Thank you. Okay, so does that help? Y'all feel something better? Good. Good. Now I'm sorry things are kind of crunched the way they are. But basically, I'm trying to get something fixed here before it puts me down. I don't want something to put me down in the middle of the semester, like a flat tire, you know, or a blowed head gasket. Let's say a blowed head gasket. I don't want to have a blowout. And that's kind of what's causing this crunch. So, but in reality, listen, you're only missing two days. I pushed this thing slammed to the end of the year so you wouldn't miss much at all. Very little. So it's doable. It's doable. Let's go back. Yes, sir. My plan, they'll have me walking the same day, but they won't let me come back out here for 6 weeks because of the therapy and all. But they'll go in there and do what they're going to do to repair it, and they have you walking the same day. So my plan is to be back out here January 4th when they reopen, and be ready to start with a better back.
You said on the message that you were going to write down that you want to register for next semester.
Yep. If you want to register, I can do it after class. I can do it like today. If you want to do it now after class, I can do it right in here. Yeah. Or if you want to tell me what class you want to take, if you know what you want to take, I can register you on my own to do it.
Yeah, I'm just going to take that automation.
The automation class. Okay. Is there anybody else in here that knows they're going to take that night class, the ELC 215, Victor McGill? ELC 215, you've already had it. Motors and controls. It is. It'll be 4 days a week. Motors and controls will be here's my classes right here. I'm going to tell you what I'm doing. And if you want to take any of them, let me know and I can sign you up. Monday through Thursday, it's actually 4 days. 12:30 to 1:55. Now, this is the first time I've done a 4-day class in curriculum, and it had to be done that way. They couldn't make it work with these other new programs with HVAC and the electrical degree. This class works in 2 degrees. It works in this one and the new electrical degree. And we got to accommodate other folks that are taking a whole nother thing. Yeah. It'll be that part is going to be in person. There'll be an online portion for your assignments, for your Moodle work, but it'll be, that amount of actual hands-on. Some lecture and a lot of hands-on. I'm also teaching hydraulics and pneumatics, HYV 110. That's Tuesday, Thursday, 3:30 to 5 p.m. And then ELC 215. Tuesday, Thursday, 6 o'clock to 7:55. So that's my 3 classes there.
That's that. Automation.
It's called electrical maintenance, but it's for automation systems. It's advanced PLC for what it is. Plus the mechanisms, it's mechanical and everything all together, conveyors, actuators, grippers, vacuum tools. But it's PLC. So it's a focus on the PLC. It's an emphasis on that, but it includes a lot of pneumatics, a lot of actuators, a real moving line, real running line that I put a lot of bugs in. So it's a factory automation line that you learn how to troubleshoot. It's already programmed, already wired. You're stepping into it like stepping into a new plant. You learn how to read all the schematics on there, how to go online with the right IP address to the right station, view the ladder logic and find the problem and show me what the problem is with a meter and with a laptop. So there's a lot to it. It's very, very good stuff. You'll like it. Okay, so McGill, you want me to put both you guys, you want to be for ELC 215?
Can you put me for 117?
117? And Roger? Correct, okay. So I got y'all 2 down for 117 and y'all 2 down for 215. If any of you know for sure you want to take something, let me know. I'll go ahead and get you registered because they're worried about numbers. They're already sending an email out saying they're worried about numbers because numbers ain't looking too good. But it's natural for them to look at them early, and be concerned. Do you want to take that night class or not? And no approval yet. Yeah. Tell them that it's go in there, take your phone, take some snapshots close up of the panels and the actuators and stuff, and show them that you'd be getting into advanced Ethernet network PLCs. I know some of your phones are probably Ethernet and tied to the internet probably. So it would help you. It's put you on another whole level with PLCs, another whole level. You're sitting right here right now. It's going to fuel right here. I ain't kidding. You ain't seen nothing as elaborate as that. Not yet. And you could really sail with it good. Okay. So next one. Let me go back and make sure I got my screen share right. Brandon, you still with us? No, he ain't with us now. He can catch the recording later. Now, so A conductor has a resistance of 10 ohms. So many feet of wire, they ain't telling us how many feet. But a conductor of the same material, but twice the diameter, okay, diameter, not CSA, diameter, will have a resistance of what? Now, this is kind of a trick question. And the reason why I say that is because the diameter is one thing, but the CSA would be the diameter squared. When you square the diameter, it becomes the CSA, okay? So CSA is not the same thing as diameter, okay? That's what you got to keep in mind here. When you square that, it would equal the circular mills, okay, or the CSA. The CSA in circular mills. CSA is measured in circular mills. So the way you have to reason this out is like this. Well, this is referred to if you go back to page 68. And let me get my thoughts together here to say it the right way without confusing anybody. Yeah. So the way you have to reason that out is like this. You have to say, we're going to do two examples here. If you take the example on page 68, they're saying that if you have a wire with a diameter of 1/100th of an inch, if 1/100th of an inch would equal this. In decimal, it's 0.01. That's 1/100th of an inch. Okay. Now, when you're measuring wire, you would express it in thousandths. You can put a 0 on there, and 10 thousandths is the same thing as 1/100. So these two here equal. Okay. Now, when you look at 10 thousandths would actually equal 10 mils. When you look at a mil foot of wire, 1 mil foot of wire. Let's say this. For every thousandth of an inch that you have, you have a diameter of 1,000th, that's considered to be 1 mil foot. Now, if I have 10 thousandths of an inch, which I do, it's the same thing as 100th, then I actually have 10 mils, don't it? It's 10 mils. This would equal 10 mils. When you convert diameter to mils, so it equals 10 mils. Okay, now, to get the CSA, you square that. You square 10 mils, which equals what? It equals 100. 100 circular mils, 100 cm. Now, when we double this, I'm not getting my. Let's go back to the camera here for. Always got to keep in mind here who's watching. Watch this real close here. If we double this and we say 2/100ths of an inch, I say two over 100. Would be that, right? In decimal, it would be 0.02. Now, we throw another zero in there to talk in thousands, because you got to talk in thousands with this. This equals this. When you add a zero, it doesn't change the value of that. You know, 200 is the same thing as 20 thousandths. So 20 thousandths is the diameter of this wire. That would equate to how many mils? With 20 thousandths would be how many mils? Would be how many? 20 mils. Now, if we're going to square 20 mils to get the CSA. So if you square 20, what is it? Hmm.
400.
400. 400 circular mils. But here's what happens. Watch closely here. This is you really got to slow down when you look at this. Reason why I'm going over this. When you double the diameter, going from 100th of an inch diameter to 2/100ths of an inch diameter, you're going from a 10,000th diameter to 20,000th diameter. You double the diameter. But what happens is when you square it, the number quadruples. So when you double some number and you're squaring numbers, just by doubling some number, the answer quadruples. It doesn't just double, but it actually quadruples. That makes sense?
Mm-hmm.
It's a torque wrench.
In a tool room.
In a tool room, that
Mhm.
box.
Yeah, when you go in the tool room, all the way over the second camera and over, open up in the bottom, there's a blue thing, a blue case. That's the one we use, and then there's a big red one you can shove it. It's like real heavy.
Where was that box of the valves that we were taking apart and had like the stuff inside, the baffle inside? Like,
Back in that cabinet
I can't find that box. Those pieces that we all took apart and showed you the inside.
of the valves,
Yeah, I didn't.
they were in a bucket in the bottom of that cabinet back there. Remember that bucket we looked at?
Those weren't the same ones last time, like Steve.
You know, the steam valve, the stainless steel valve, the one I showed you the other day, with the tank is in it.
The other one.
The flapper check, you mean?
Well, like it had like the flapper check and then had a couple other ones that they pull out. It wasn't the ones in the bucket.
And they're not, you don't see them in that
I
cabinet in
don't
there?
see them in the cabinet, no. They were just in a box. There was a few.
The only ones I know is the ones in that bucket in there that we looked at. The small ones and then whatever else is in there. Other than that, I don't know.
Yeah. All right.
Somebody may have moved some.
Yeah, no, it was just, I forgot. It was more or less along the lines of all steam stuff that they were able to take apart and look at.
Well, that was the traps.
That
The
was
steam traps. But this is not,
okay.
you're not looking at traps today, are you?
No.
No, that was traps.
Okay.
That was traps. That was in the steam plant.
That's right. You know, the other.
Yeah, you're not dealing with traps in that. Yeah. That's the steam plant. Yeah.
All right.
Yeah.
All right, thanks.
10-4. Yeah. Yeah. He's learning. He's helping me cover butterball. He's teaching on valves right now. He's thinking about steam traps, but that's not in the valve book. That's in the steam book. That catches the condensate and steam lines, and they'll flush it back to your feedboard tank. Do y'all have traps out there to catch condensate in the steam line? In your distribution lines for steam, you have condensate in them lines, and the trap will catch it. And it'll dump it right back to your feed water tank to reuse it. Yeah. Okay. Anyway, you see how that works there? Okay, so now let's go back to the back to the worksheet. Let's go back to oodles and moodles here. Well, my computer is kind of like me. It's got some lag. So a conductor has a resistance of 10 ohms. And then when you double the diameter like we did, then what would the result be? If we had if we had 10 thousandths here and we went to 20 thousandths diameter and it quadrupled, it's gonna quadruple in that case.
So 20 ohms.
Hold on.
I think.
What? Hold on. Hold on. Let me get my brain together here. We got to have more in our thinking here than just that alone. Let me get my thoughts in order here. Yeah, so here, look, watch this right here. This is solid right here. When you go back and you look at the resistance formula, which would be R equals what? What's the formula for the resistance of a wire?
R equals KL
KL over CM. Now you've got a picture of this. You've got the picture of this right here. If we know, listen, if we know that the circuit of Mills is going to quadruple, and we quadruple that bottom number, and we're sitting here at what, 10 ohms? Exactly. Listen, you have 10 ohms there, and you're going to quadruple that number, then it's going to cut it in a fourth, right? The resistance is going to go down to a quarter of what it was. Your circuit of Mills is going to go up times 4, but your resistance is going to be, because the circuit of Mills is on the bottom end of that formula, that 10 ohms is going to be divided by 4. It's going to cut it in a 4. Does that make sense?
Mm-hmm.
Exactly. The only way to see this actually is to do what we're doing right now with some kind of an example, and that's the only way to really see it. You know.
Okay, I'm missing something. I've missed something.
Okay, kind of. At what point do you? Let me kind of.
When we get to the, all right, when you get to the CM, all right, I understand the original one has 10 ohms. That's where you got your 10. But for the CM, how did you get the 1/4? Because you doubled with this.
Yeah, when we doubled the diameter, when we went from 10 thousandths to 20 thousandths diameter, that caused the circuit of Mills to quadruple.
Gotcha. Okay.
And listen, because you're squaring it. When you quadruple that number, and then you plug in a number down here that's 4 times bigger than what it was. What's it going to do to that? It what? It'll reduce it exactly 4 times. It will, because of where it is in the formula. Because it's on the bottom. It's on the bottom of the formula. It's like putting a 4 in there, and you know it's gonna divide that by 4. That's the only way really that you can see it. It's too much to it That's why I said this chapter is so important. And I can tell you, you need it. I don't care who you are in the electrical field, you need this stuff. I'm telling you, you really do. Yeah.
I can't find it.
Can't find
Yeah.
what? The torque wrench.
Yeah.
Okay.
Sorry to interrupt.
Hey, you know what? Got the carpets in our classroom?
I did. There's nothing on that.
See a blue torque wrench? It's about that long. If you in classroom,
Oh,
it's
no.
130.
Oh,
It was in there. You understand?
I can get common sense. Make those imaginary numbers. That's what I'm doing on these. If you got to know that number, these numbers every time you square it, so you get one. That's why. Don't say nothing. What? You know what I'm saying? So you divide it by order. Nowhere in that book.
I've been not reading, don't know nowhere.
Yeah, that's what's on the list. What's he trying to find? So, well, it's not on what he's explaining to you. That's why he showed that, say, the CM or the diameter is twice as big. The formula, the question in the book tells you is double in size. So, in order to get the numbers for it, it's double in size. You got to know that when you take the square root of it, it's important. You always get the Army style. It's wrong. It's wrong. But besides that, if I were to use like point, three for that, and then I dealt with the 160, it would still be like the 2.5. I mean, it's good. I guess it's random numbers. Yeah. I mean, but the reason he specifically used that is because that question specifically said it's double size. That's what you get to. So you're assuming it don't matter what size it is because it's equal size. You're just assuming because it's double size. So that's how it comes up. To show you that it's quadruple. See, that's what I was trying to understand that. That was just a number. It didn't matter about that. No, that's because that little part of the question said that it's double the size. So it really don't matter what number you use. If you put in 0.555,
It's not long how for everything is.
you double that.
Okay, so tell me kind of what are you thinking now? Does it make sense? Does that make sense?
Absolutely.
Absolutely.
Roger explained.
Okay, good. Because sometimes a student can say something slightly different to me and make it hit home. So go for it by all means. Everybody cool? Brandon, are you still with us?
Yes, sir.
Okay, do you see the oodles and moodles up here?
Yeah.
Okay. We gotta laugh better than crying, man.
Yeah.
Right?
Yeah.
Me and Reuben Caswell, when they told us way back, they said, look, you guys got to start putting your stuff in Moodle. And me and Reuben frowned. We poked our lip out. And I said, well, we ain't going to cry about it. We're just going to do it. And I said, you know what? Moodle. That sounds like noodle. And I said, you know, it sounds like oodles or noodles, you know. I'm just going to kind of have chuckle about it and call it oodles and noodles. You know, and we're just going to do it and learn to love it, you know.
Yeah.
So actually now it's a lifesaver. Yeah, we're going to hit the high spots on, we're going to hit the high spots. So.
Yep.
Okay. Yes.
Would you just take the square root of 311,000 and then move your decimal point over 2 spaces?
When you go, let's do that together. Exactly. When you go in reverse, if you take the diameter and square it, that gives you the circle. You got to go in reverse. You got to do the square root. The square root of that, and then you got to move the decimal over. Divide by 1,000, and that takes it back to diameter. It takes from mils back to diameter.
Okay, so this one you're going to find the square root of.
Yeah, let's go through the steps. That way, nobody gets tripped up on it. Yeah, that's why it was so important for everybody to participate today, because this stuff is tricky, man. It really is. And we don't have much time to get it down pat. So we want the diameter equals what in inches, and we have a CSA of 311,000 circular mils. So the first thing you want to do is get the square root of it. And what does that equal? 557.67373 mils. Now look, when you do the square root, you're actually in mils. You're not in thousandths yet, right? You're in mils. When you go in reverse from circular mils, then you go back to mils. And to go in reverse of that, if you have 557 mils, listen, that would represent in diameter 0.55767, so on, inches. You got to divide by that to get back to the actual. Right, by 1,000. You have to go by 1,000. Because look, one circular mil equals 1,000, right? Look here. Go back to your basis here, and look, 1,000th diameter equals 1 circular mil.
Put your regular mils there, not circular mils.
Right, it equals a mil, but when you square that, it's 1.
All right.
When you square it, it's 1. Now, when you get beyond 1 and you square it, then things get different. But when it's 1, it's still 1 when you square it. And let's go back in reverse again. Let's go in reverse from right here. So listen, if you take this number right here How do I find out the CSA of this number? Let's go in reverse and let's just see it work the other way. Okay. If we take that diameter right there and we want to go in reverse, what do? We know that for every, that for each thousandth of an inch, it's a mil, right? You can say it's roughly 578, you know, just take that actual literal number there. Take that literal number right there. And how many, in this case, you would have to just basically, you could say 577.67 mils is what that would be. In mils, that right there would be, for every thousandth, it would be 1 mil, right? For every thousandth of an inch would be 1 mil. Here you're dealing with 577 thousandths there, and then some. So even if you round it to 578, just say 578 mils. Just around it, okay? That many mils. And then you square that. Then it's going to come up with something close to that. And I chopped some numbers off. What does that equal if you square that? Yeah, it throwed it off some. It throwed it off some. So actually, if you were going to keep it exact, it would need to be 577.67 mils. So if you keep the exact number there and square that, square 577.67, see what happens. 0.311. 0.311. If you took that and squared that, you're getting what? 333,000. We better keep all them numbers in because we've lost something when I chopped it off. Look, I sure did. I transposed wrong. I transposed wrong. That's me. My brain's just too scattered right now. Look, 557.6737 373. If you go back to that, you got to divide that number by 1,000. You have to do that, okay? To go back, we're going in reverse order, so we're multiplying by 1,000. Basically, you're multiplying by 1,000 to go in reverse whenever you divide by. We're going to multiply by 1,000. So if you take this number and you square it, what does it equal? Right. So you end up coming right back to this, don't you? Yeah. Yes, sir. So that's what it is. You just can't round any when you're going to go in reverse. You can't round any. All of these numbers really affect it. You can't chop anything off if you're going to end up going in reverse right back to what you started with. So basically, the gist of it is this. The physical diameter of the wire would be 0.57767, the real diameter, if you measured it with a caliper in inches. And then you take it and you multiply it by 1,000, which becomes this many mils. And then you square that number of mils and it becomes this in circular mils. That's if you're going from diameter that way. If you're going to go in reverse, then you get the square root and then divide by 1,000, and that takes you back to the diameter. So that's okay. Everybody okay? And then if we go back, let's back up because there's other ones that concern me. How about number 4? A conductor has a resistance of 12 ohms and the second conductor has the same material the same CSA, but it's 4 times as long. And so what would be the resistance if it's simply 4 times longer, but it's not any bigger? Okay, I heard one person say 3 ohms, but look at it closely now. You got two conductors there. They're the same diameter, the same CSA, the same material, but one of them is 4 times longer than the other one, the length. So what do you know about the length? The length is directly proportional to the resistance, right? So the longer you go, the higher the resistance is direct. So the book says, if you go to page, what page does it say? If you double the resistance, if you double the length, you double the resistance.
So that'd be 48 ohms.
That's on page 67.
Right on 67, it says exactly. Thank you, Renee. You want to read that out, Renee, for everybody?
The resistance of Walmart.
I need something from Walmart. I forgot what it was.
This is very critical stuff that we're dealing with. This is just so important. We've got to slow our brain down on this thing. So when you double or triple or whatever on that length,
No, I need a couple quarts of oil from well, never mind. I'll get it later.
That's why it's so important in hog houses that when you're running them long runs, chapter 9 is going to be a real eye opener for you, Jamie. You're going to be a guy that can go out there and tell somebody, contractor up front, if they're not doing this. You can plug some numbers into a formula on footage and amp requirements for that farm, and you can plug some numbers in, and it's going to kick you out a CSA that you can use to get a gauge off of and be exactly dead on for the wire for that long run, and you will not have a voltage drop issue, guaranteed. You won't. No embarrassment. You ain't gonna have to go back and pull new wire. A friend of mine, Wayne Naylor, he sold a bunch of controls to some farm years ago in Middle Control. That farm was a long ways off the highway, and when they installed all that equipment that they bought from him, they told him, they said, Wayne, all of your stuff is, none of it's running right. If every bit of it, the fans are running slow, nothing's running right, we need you out there. He said, is that right? And he went out there. He knew what was up. He got a voltmeter. He checked voltage at that hog farm. He says, you don't have enough voltage on this building to run this building. You got a voltage drop from that highway. And man, you talk about embarrassment. That was whoever the contractor was they didn't calculate what you're getting ready to learn in chapter 9. And it's worth $1 million for you to know this. You can be the hero. I'm serious by knowing this. I'm not kidding you, man, because everybody doesn't know this stuff. It's actually on the internet. You can get it easy if people dig for it. And you're going to get it in here. So, okay, everybody, cool. Now, right on. That's very simple. Everybody okay with that one? What do you think number 4 would be? Right. Exactly. What about number 5? CSA is measured in what units? Okay.
Mills.
Well, is it just mills?
Or no. Circular mills.
Okay. Now, by mathematically squaring the number of mills and the diameter of a wire, the result is right. The number of separate conductors in a raceway, which could be conduit or raceway, is a major factor in determining. Now, we haven't talked about this, and we got to talk about it now. This is a super big one that I gave you a handout that's going to explain this, and you got to have it. The number of separate conductors, let's say in a piece of conduit, it helps to determine what. And now, let me show you something in the code book. We're going to flip over, get that handout I gave you. And this is going to be something that was not explained very much in the chapter. So we got to flip over to the electric code. This is very much needed. Here's another one that can be that a lot of folks never look at. Now that let's say, for instance, Jamie, that you were using, maybe you were in the center column here, or maybe you were even over here, maybe you were allowed to use that column there, and you're using a number 8 wire for the pressure washer, okay? Number 8, you can pull 55 amps off of that wire. Now, it's conventional, and it's conditional on this. Look closely here. What does it say up here? The allowable ampacity or amp rating of insulated conductors rated up to 2,000 volts and between this temperature range. Listen, not more than 3 current carriers wires, not more than 3 in a raceway, a cable, or directly buried, which means this. The only way that you're allowed to pull 55 amps from that wire is if there's no more than 3 current carriers in that conduit. If you have another wire or maybe 4 wires or more in the conduit, you have to do a derating factor, which means that you can't draw that much in there. That's because of heat buildup. The more wires you put in conduit, the more heat trapped in there and it can't dissipate as easily. So you have to derate the current rating of the wire, and it's based on this. So the handout I gave you, watch this right here. Let's flip on. So the 55 amps that you have right now, Jamie, for that pressure washer is going to turn into this. Flip on over to that table right there in the handout I gave y'all. And Brandon, I put this PDF in there in the same section where this worksheet is. You can download this to your phone.
Mm-hmm.
It's National Electric Code. It's a packet that's got six sheets in there. So we're on the third page. We're on the third page right now.
Okay.
Now, catch this right here. This is like super important. Well, let's say, for instance, that in that conduit, Jamie, you got 6 wires, between 4 and 6 wires. Look, you can only use 80% of the amp rating of that wire. 80%. You have to do an adjustment factor because of the number of conductors. If you got between 7 and 9 wires in that conduit raceway, you got to multiply the amp rating by 0.7. If that number of wires is in there, you take the 55 amps times 0.8. And then what would it be then if you said 55 amps times 0.8? So then you couldn't pull for 44 amps without having a risk of wires melting and things like that. Now, what if you had, say, between 10 and 20 wires in the conduit? You got to say 55 amps times 0.5, 50% of it is all you're allowed to draw without having overheating in there and a possible melting in the conduit. How many of you that have jobs already have seen melted wires in conduit? I see 2 hands, 3 hands, 4 hands. There's 4 hands out here of people that say they've seen melted wire, including me. That's 5 of us seen melted wire, like melted wax in conduit. I pulled them out before because of issues like what we're talking about that were not planned properly. Things weren't planned properly. It's very embarrassing, very costly, to that. Damaging equipment and downtime and stuff. So this here, you really should, the PDF I have in Moodle, download it to your phone. You can have it on your phone, very easy. Your phone will read PDFs. So I would advise having that, share it with other people that you work with. You can, Jamie, you're turning into an instructor. Teach them guys out there where you're at this stuff. Just turn it on around and show them what you're getting. Okay, everybody cool with that? So in view of that, another thing, listen, while we're at it, if you back up here, look, you back up to page 2. Actually, go back to the main chart here. Let me show you another factor that changes, that reduces the amp rating on the wire. Watch this. These numbers are based on, listen, an ambient temperature of 86 degrees Fahrenheit in the room. So listen, you can pull 55 amps for that wire if that room is no more than 86 degrees Fahrenheit. So what happens if that room is 105? If it's an air compressor room, it's really hot. Okay, look, go to the very next page, and you have a temperature correction factor that you have to put in place. This is stuff you gotta know if you're ever gonna get licensed. If you're ever gonna get electrical license, you have to know this stuff. Now, let's say the wire that you have here was a 90 degrees Celsius rated wire, but the ambient temperature, I'm gonna let you give me a real ambient number for the hog house. What could it possibly be in here? 110, 100, 100, okay. So if the ambient temperature in Fahrenheit is about 100, it's going to be in this range here, right? And look, you have an adjustment factor of 0.91. Here's what that means. You got to take that 55 amps that you're supposed to draw times 0.91, and it reduces it by that much because of the temperature of 100 degrees in that room. And then you also got to go in there, listen, and you've already reduced it by 0.91, right? Then if you've got, say, 4 wires in the conduit, seriously, this may sound ridiculous, but this is the way it has to be done. After you do that 0.91 times that 55 amps and you get it reduced down, you take that new answer that's reduced. What is it right off the bat? Somebody tell me. Say 55 amps times 0.91. So it's got a calculator. We're taking a wire size that can draw 55 amps. 50. So let's just show you what happens to a piece of wire. What happens when you have a hot environment and then you have several of them in there. We started out with 55 amp capacity, right? Now you got to multiply it by 0.91, and it gives you what? You said 50 amps. Roughly 50 amps. 50 amps. Now that's because of the temperature of it being 100 degrees. This is an adjustment factor. Now let's say that you got maybe 6 wires in the conduit. You got to multiply this answer by 0.8 times 0.8. What is that? I'm serious. If you go take a code class, man, I mean, Jake's teaching some code stuff. It's how much? 40 amps. You can ask anybody teaching electric code, and that's the way it's done. So you're not supposed to draw no more than 40 amps off of that wire. If it's 100 degrees in that hog house, and you got, say, between 4 and 6 wires in the conduit. Make sense? This is the way the electric code works. It is. You have to do it twice. It based on temperature adjustments and on the number of wires in the conduit. That adjustment too. Yeah, correction factors and adjustment factors. Yeah, exactly. Okay, so Thursday we're going to pick right back up in here, and we will try to go over the rest of this. If anybody has any problems with it, let's try to iron it out here. Okay, so that there's not issues when you're by yourself. And we'll try to finish up whatever labs that need to be done.
All right, got a question.
Mhm.
It says the resistance of the wire is directly proportional to the answer is the length, but the length ain't on here.
Right, so there's another thing in there that is true.
Is it on the paper or in the book? I can't find it in the
It's in the
book.
book.
I can't find it in there.
So you're on number,
I only got 2 questions left. Got this one left too. I can't figure it out either.
right, let's flip to it so it can be a help to somebody else too.
10.
Right, let's go ahead and flip to it because I'm gonna use it for a teaching moment here. Ten.
Yes, sir.
Now, the resistance of a wire is directly proportional to, then we know it's proportional to the length, but that's not included in here. So if you go in your book, go to the last page that talks about temperature, page 70. So on 70, the resistance, blah, 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 let's see.
If the temperature rises, it causes an increase in resistance.
Right. If the temperature rises, it causes an increase in resistance, which means it's directly proportional. Yeah, that's it. Yeah. That's why when you go back to the resistance in your K factor goes up when the temperature goes up.
Mm-hmm.
Your resistance for a mil foot of wire, it goes up when the temperature goes up. The copper, it has more resistance. You know, that shows if you go back to page
It's on page 68 and 67.
right. So in other words, copper wire, a mil foot of copper wire is 10.4 ohms at 68 Fahrenheit, but that same mil foot of wire is 12.6 ohms at 167. So the ohms goes up for that same wire to go up in temperature, and that's the answer. Yeah. This stuff is it's very good stuff. It's good, very good stuff. You know.
I have a favor to ask.
Mhm.
I know that you said you wanted everything done tonight. Can I push mine back till tomorrow?
Mhm.
Because I have to work tonight.
Yeah.
All right, thank you. Thank you
You're
so
welcome.
much.
Yeah. What I'm trying to do is get stuff to where people are not waiting to the last minute. Because once we get to the end of the gate of it, it's going to be a lockdown.
Yes,
It's going to be like Noah's Ark.
I know.
And people was outside beating on the door trying to get in. That flood coming. It was like they couldn't get in. You know what I'm talking about? I'm talking about, yeah, it's like Noah's Ark, man. And that door shuts, and we can't open it up.
All right.
Yeah.
So,
Yep.
tonight, and then I'll take tomorrow off and work on it. All right. Thank you.
And you're welcome. You're doing good. I'm glad you took the course. You got a good head for this. You do. You do. I'm glad to see you in here. Yeah. Okay.
This will be my answer right here. I'll tell you how I got it fit. So I divided 17 by 1,000, and I got 0.017. I squared that, and I got. Hold on.
Which one are you on?
13.
13.
I squared that 0.017. I got that number. Multiply it by 1,000. 0.289.
Well, but you can't square go back to where you started at, though. You started with what now?
17 divided by 1,000. That's what it wanted.
Right. That's the
1,000 of
actual
an inch.
diameter.
Yes, sir. And then
But look, so that's in thousands. How many mils is that? If 1 mil equals 1,000, and that's
it's
17.
1.7.
No. If you go back to right, you got a diameter of 17 thousandths.
Mm-hmm.
So if you look up here, if 1,000 is 1 mil, if 1,000 is 1 mil, you got 17 thousandths. Is how many mils? 17. And the 17 is what you got squared. Mm-hmm. You got to convert the diameter into mils by dividing by 1,000.
What was I doing? I was doing circular mills then, right? That's what I was doing, but that's not right.
Well, to do circular mills, look, you got to take your diameter, okay, of If you got 17, if you have 17 thousandths diameter,
Mhm.
then it equals how many mils?
17.
17 mils. And then you have to square that to get circular mils.
289.
Exactly.
All right.
This is the crossover deal that can get overlooked here. And look, actually, when you go to mils, you actually multiply by 1,000. You're going to multiply by 1,000 to get mils. No, yeah, you multiply by 1,000. The diameter, when you get the diameter in inches, you multiply by 1,000, and it gives you mils. It goes from thousandths to mils, because 1 mil equals that. This is how you know that.
Yes, sir.
Basically, by multiplying by 1,000, it converts into a mil.
Yes, sir.
You know, when they say the mil thickness on something, like if you paint a car, a classic car, and you paint it, and that paint is so many mils thick, 1 mil is a thousandth of an inch. You know what I'm saying?
Yes, sir.
They measure paint in mils. Or coating, if you coat something in plastic, it's actually measured in mils. Oh, yeah.
All right. So is this what we're going to be doing Thursday?
We will need to go over, if anybody has any questions about this one, then we'll go over it, and then we need to be going into chapter 9. We'll probably wait until Tuesday to go to chapter 9. If it's going to be, it's probably too much to rush to do. Let's see, today's 27th. So if we do, yeah, we can just wait and do chapter 9 on Tuesday.
All right. I didn't know if I needed to call in for work Thursday or not. I just finished that worksheet.
But if you
Chapter
finish that, and if you're caught up on lab, then you're fine. And we'll just keep a lookout for chapter 9, because I won't have it in there by this Thursday. It'll be in the weekend.
All right.
And then we're going to cover it Tuesday.
All right. So I'll wait
Just like
till
we're
Tuesday.
doing right now. We're going to be right back in here doing it Tuesday.
All right.
For
That's
chapter 9.
all right.
And
Thank you, sir.
the worksheet, I'll have it in there sometime the weekend. You can even start looking at it.
All right.
But don't submit nothing till you're in here. You know what I mean?
Yes, sir.
Because there's a lot to it.
Yes, sir.
Yeah.
So we're going.
Hmm.
See you, Mr. Wood. Thank you.
Yes, sir. You're welcome. Okay, so yep, nobody left in there. Okay, we're gonna go back. Back to here. And let's go. Okay, so we're going to end the video now. So whoever may be watching, thank you for watching. And again, go ahead and work on the worksheet that's in Moodle for chapter 8, and read that chapter. The handout that I gave a paper copy out today that contains the wire chart plus correction adjustment factors that we looked at for temperature this high, or for a large number of wires and conduit. All that stuff is in this handout here, and you can download that. It's in the same. It's right beside the worksheet in Moodle. So this electric code stuff that shows those charts for doing the adjustments based on temperature and all that. It's in that one PDF so that you can download. You can download to your phone or your computer. So this is the table that shows the adjustment for how many wires that you have in a conduit, adjustment factors there. So all that's in that same PDF document with the wire chart. So you need that one as is a definite. I'm going to end the recording now, and then let it process so I can put it in YouTube. And thank y'all for watching. If you have any questions, you can contact me at dking@sampsoncc.edu. And it was a pleasure presenting this, and hope it's you've learned something, learned a lot. You can let me know if you're a student, you have my cell number you can call, or if you're a viewer from outside the school, contact my email, and I'll make contact with you and help you answer questions you may have, and maybe we can get you to come take classes with us. Got a lot of good stuff going on here out here at Sampson Community College. We have an industrial systems program that includes a lot of electrical that I'm teaching. It includes hydraulics, pneumatics, gear drives, belt drives, chain drives, some machine shop, little refrigeration, some welding, a lot of stuff, alignment, shaft alignment, pumps. So the industrial degree covers a lot of stuff for multi-craft type people that are in high demand in Sampson County. If you would rather focus on electrical, we have an electrical certificate you can get in 1 year, or an electrical degree you can get in 2 years if you come full time. And we also have other things. We've got HVAC program, brand new, get a degree in HVAC. You can get a degree in welding. So we have lots of stuff that we can equip you with in your career if you just contact us, and I'll help steer you in the right direction based on your interest. Okay. So thanks for watching. God bless you. And this is Durwood King of Sampson Community College, and you have a nice weekend. Well, a good week, because it's Tuesday. We'll be back on Zoom Thursday.